Good day, the topic is analysis of gravity dams. Dam is a massive structural barrier that serves as a block to prevent flow of water. The image is a sample of a dam, the Amboklao Dam. And some purposes of dam construction are for water supply, irrigation, power generation through turbines or turbines, and flood prevention. For the different terms used, first is the word upstream. It is the side of the dam that holds water according to its design capacity. It has higher elevation of water. Next is the word downstream. It is the side of the dam where the excess water flows, often with lower water elevation. Then we have the word heel, similar to a foot. It is the point at the lower back edge of the dam at the upstream side, while at the other point it is the toe, and it is the critical point of the dam. The terms for soil foundation, we have permeable soil, which means porous soil that permits flow of water or infiltration of water. Also, we will consider an uplift force or pressure at the base of the dam. And the other term is impermeable or impervious soil. Means soil with relatively small voids or no voids that do not permit flow or infiltration of water. And for this case, hydrostatic uplift is negligible or it is equal to 0. Then let us take the analysis of a gravity dam. First, assume a unit length of the dam, so which serves as a representative length for the analysis that is either 1 meter or 1 foot. Second, draw the free body diagram or FBD of the sample section. For weight of the dam, divide two simpler shapes for purpose of centroids at the latter part of the analysis. For this sample, divide to two shapes, one rectangle and one triangle. Thus, W1 for first shape and W2 for the second shape. For hydrostatic forces, consider only the portions exposed to water. For inclined or curved surfaces, better to consider components of the hydrostatic force. Sample is the forces at the downstream side. If the foundation soil is permeable, then determine first the pressure values at the heel and at the toe. For simplified analysis, connect with straight line and determine the hydrostatic uplift. Take note that the pressure and uplift force are perpendicular to the base of the dam. And if the foundation soil is impermeable, then hydrostatic uplift is 0. Third process is to determine the reactions at the foundation. For horizontal reaction or R sub H, assume direction opposing the force at the upstream side. Now, let us apply some forces horizontal equal to 0. Due left is equal to due right forces. Forces that are due left are R sub H and F sub HD, while force due right is F sub HU. Rearrange, therefore, R sub H is equal to F sub HU minus F sub HD. For vertical reaction or R sub V, assume upward direction. Apply some forces vertical equal to 0. Upward equal to downward forces. Upward forces are R sub V and U, while downward are F sub VD, W1, and W2. Rearrange, therefore, R sub V is equal to F sub VD plus W1 plus W2 minus U. For the fourth part is the location of the reaction represented by X bar. Let us sum moments at the critical points at the toe. Clockwise equal to counterclockwise moments. Then, let us represent counterclockwise moments as Rm for this orientation of sample section. Therefore, for resisting or righting moment, these are moments due to forces that is responsible for keeping the dam at its stable state. Example are weight of the dam, hydrostatic forces at the downstream side, and in addition, if we have vertical component force at the upstream side. Next is to represent clockwise moments as OM for this orientation of sample section. Therefore, for overturning moment, these are moments due to forces that causes instability of the dam, either sliding or rotation of the dam about its critical point, that is the toe. Example are horizontal force at the upstream side and hydrostatic uplift. Therefore, the clockwise moments are R sub V times the moment arm X bar and group of OM. And counterclockwise moments are the group of RM. Transpose OM at the other side and cross multiply RV. Therefore, X bar is equal to RM minus OM over R sub V. For the fifth process, let us now assess the determinant if the dam is safe, the factors of safety. For the factor of safety, it is the ratio of the resisting factors over the generator or cause of failure. The resisting factors must govern. Therefore, for some notes, if Fs is greater than 1, therefore the resisting factor govern, it is safe. But if Fs is equal to 1, it is critical. And therefore, if Fs is less than 1, it is unstable or failing. And for the analysis, consider only actual forces, reactions not included, but used for sliding to represent the group of forces. First factor of safety is against sliding, or Fs sub S. Fs sub S is equal to the resisting force, the frictional force at the base of the dam for the numerator. And cause of failure is the pushing force Fh net for the denominator, where frictional force is mu times Fv net, where mu is the coefficient of friction at the base of the dam, while Fv net is the remaining downward force after subtracting upward forces. For Fv net, from all the vertical forces, the remaining value is equal to the reaction vertical, or RV. While for Fh net, from all the horizontal forces, the remaining value is equal to the reaction horizontal, or RH. Updating the equation, Fs sub S is equal to mu times Fv net, or RV, over Fh net, or RH. And the conservative factor of safety for the sliding for the design is 1.5. But as long as Fs sub S is greater than 1, ideally it is still safe. Next factor of safety is for overturning, or Fs sub O. Fs sub O is equal to the resisting moment for rotation the resisting or writing moment, or RM for numerator, and cause of rotation, the overturning moment, OM for denominator. The conservative factor of safety, or FSO, value for the design is 2. But again, same as against sliding, as long as the value of the factor of safety is greater than 1, ideally it is still safe. Last part is to define the design pressure at the base needed for the design of the dam footing, and this be compared to the bearing capacity of the soil to check if the soil can carry this massive structure. So for the pressure, we will consider only the value of the vertical reaction, or R sub V. Consider the projected rectangular surface of the base, assigning the center of gravity, center of pressure where RV is concentrated, and distance from CG to CP, the eccentricity E. Apply the concept of combined stresses from strength of materials. That is, for axial, we have P over the distributive area A. And for bending, we have moment M of the axial force with respect to the centroid multiplied to C, the farthest fiber distance from the neutral axis, over the moment of inertia of the projected surface about its neutral axis. Substitute RV for P, B by sample length for area A, RV times E for moment M, B all over 2 for farthest fiber distance C, 1 all over 12 times sample length acts as the base since it is parallel to the neutral axis, then multiply to with B raised to 3 that acts as height which is perpendicular to the neutral axis for our moment of inertia I. Simplify by extracting RV over B by sample length. Therefore, Q is equal to RV over B times sample length multiplied to the quantity 1 plus or minus 6E all over B, where RV is the vertical reaction, B is the sample base of our section or the dam section, then sample length either 1 meter or 1 foot, then for E, that is the eccentricity distance from center of gravity to center of pressure, or CP, then for B again, that is our width. The addition or plus operation represents Qmax or maximum pressure, while the subtraction or minus operation represents Qmin or minimum pressure. For some notes, if RV is at the center of gravity, the pressure Q is uniformly distributed, or Qmax is equal to Qmin. Next, if RV is closer to the toe, there is a chance or possibility that Qmin will be negative, means under tension, or we will consider a wrong assumed direction. For this case, we need to eliminate it and identify only the portion under compression by means of ratio and proportion, since the diagram will be composed of triangles, one under compression and one under tension. So let's consider our sample problems. So for problem number 1, a gravity dam of trapezoidal cross-section with one face vertical and horizontal base is 20 meters high. It has 12 meters base and has a thickness of 4 meters at the top. The upstream water elevation stands 2 meters below the crest of the dam or top of the dam. The specific gravity or specific weight or unit weight rather of the dam material is 23.6 kilonewtons per cubic meter. The foundation soil is, take note, it is impermeable. Therefore, the hydrostatic uplift is 0. So determine if the dam is safe against sliding and overturning. And we will be using a coefficient of friction at the base of about 0.6. So for our solution, first consider 1 meter sample length. Next, draw the FBD or free body diagram of the section. Divide the dam to simpler shapes and assign the weights, W1 and W2. For hydrostatic force, consider the projected surface for the value of FHU. Note that consider only the submerged face of the dam surface. Then, let us now consider the value of the identified forces, starting with the hydrostatic force FHU. FHU is equal to gamma of water times H bar times A, wherein H bar is equal to the distance from CG to free liquid surface, that is 18 divided by 2, or that is 9 meters. Substitute gamma water as 9.81 kilonewtons per cubic meter, H bar as 9 meters, and area of submerged surface 1 meter by 18 meters. Therefore, FHU is equal to 15 or 1,589.22 kilonewtons towards the back face of the dam. Next, for W1. W1 is equal to the gamma of the dam material times volume 1. Substitute gamma of the dam material as 23.6 kilonewtons per cubic meter. For volume, the area of the rectangle section is 4 meters by 20 meters. Then multiply to sample length of the dam, 1 meter. Therefore, W1 is 1,888 kilonewtons downward. Next, for W2. W2 is equal to gamma of the dam material times the volume 2. Substitute gamma of the dam material as 23.6 kilonewtons per cubic meter. For volume, the area of the triangular section is 1/2 times the net base, which is 8 meters, times the height of the dam, which is 20 meters. Then multiply to sample length of the dam, 1 meter. Therefore, W2 is equal to 1,888 kilonewtons, still downward. Next is to determine the reactions at the foundation. For horizontal reaction, assume direction opposing the force at upstream side. Then, sum forces horizontal equal to 0. Due left equal to due right force. Force that is due left is RH, while force that is due right is F sub HU. Therefore, RH equal to F sub HU, that is equal to 1,589.22 kilonewtons. Next is for vertical reaction. Assume upward direction. Then, sum forces vertical equal to 0. Upward equal to downward forces. Upward force is R sub V, while downward forces are W1 and W2. Substitute W1 and W2 as 1,888 kilonewtons. Therefore, RV is equal to 3,776 kilonewtons upward. Fourth process is the location of the reaction, X bar. Apply summation of moments at the critical point, the toe of the dam. Clockwise equal to counterclockwise moments. RV times X bar plus OM for clockwise moments, then RM for counterclockwise moment. Transpose OM at the right side and cross multiply RV. Then, substitute for RM. The resisting moments are moments due to weights. Then for OM, the moment due to hydrostatic force, FHU. Substitute values, W1 as 1,888 kilonewtons, X1 as 10 meters, W2 as 1,888 kilonewtons, X2 as 16/3 meters, FHU as 1,589.22 kilonewtons, Y sub P as 6 meters, and RV as 3,776 kilonewtons. Therefore, X bar is equal to 5.141 meters from the toe. Then, let us now consider the requirements, the factors of safety. First is against sliding or Fs sub S. RH and RV represents the group of actual loads or net horizontal and net vertical forces. Therefore, Fs sub S is equal to mu times RV all over RH. Substitute coefficient mu as 0.6. Net vertical force represented by RV as 3,776 kilonewtons and net horizontal force represented by RH as 1,589.22 kilonewtons. Therefore, Fs sub S is equal to 1.426. Greater than 1 means safe from sliding, even though it is lower than 1.5, the conservative factor of safety. Second is against overturning or Fs sub O. Fs sub O is equal to Rm all over OM. Resisting rotation moments are due to weights, while responsible of overturning moment is the moment due to hydrostatic force. Substitute W1 and W2 as 1,888 kilonewtons, X1 as 10 meters, X2 as 16/3 meters, FHU as 1,589.22 kilonewtons, and YP as 6 meters. Therefore, Fs sub O is equal to 3.036. Greater than 1 means safe from overturning. For additional part of the problem, so determine as well the design pressure at the base needed for checking the bearing or carrying capacity of the soil as well as for the design of the foundation. Consider only the value of the vertical reaction or RV. Consider the projected rectangular surface of the base, assigning the center of gravity, center of pressure where RV is concentrated, and distance from CG to CP, the eccentricity E. Apply equation Q equal to RV all over B times sample length, then multiply with the quantity 1 plus or minus 6E all over B. Solve for E, wherein E is equal to B all over 2 minus X bar. Substitute B as 12 meters and X bar as 5.141 meters. Therefore, E is equal to 0.859 meter. Substitute in equation the values of RV, B, unit length, and E. Consider the addition or plus operation. The value of Qmax is 449.749 kilonewtons per square meter. Next, consider the subtraction or minus operation. The value of Qmin is 179.584 kilonewtons per square meter. Next is for problem number 2. Problem number 2 is the same as problem number 1, but consider permeable soil, which means that we have already the value of hydrostatic uplift U. First, still consider 1 meter as the sample length. Next, draw the FBD of the section. Divide the dam to two simpler shapes and assign the weights, W1 and W2. For hydrostatic force, consider the projected surface, and for the values of FHU, but the values of the following, the W1, W2, and FHU are same as the forces identified earlier with problem number 1. But in addition, we will add the impact of hydrostatic uplift. First, we need to estimate the pressure at the base. First, the pressure at the heel or at the upstream face, the P sub U equal to gamma of water times HU or the height at the upstream face. Substitute gamma of water as 9.81 kilonewtons per cubic meter and H sub U as 18 meters. Therefore, the pressure at the upstream side is equal to 176.58 kilonewtons per square meter. Next is for the pressure at the toe or at the downstream. P sub D equal to gamma of water times HD or the height of water at the downstream face or side. Substitute gamma of water as 9.81 kilonewtons per cubic meter, but there is no water at the downstream side, therefore H sub D is equal to 0. Thus, P sub D is 0. For the hydrostatic uplift, it is equal to the volume of the uplift pressure. For the volume, the area of the pressure diagram is triangular, therefore it is 1/2 times the height, which is 176.58 kilonewtons per square meter, the P sub U, times the base, which is 12 meters, then multiply to sample length, which is 1 meter. Hydrostatic uplift is 1,059.48 kilonewtons. Next is to update the reactions at the foundation. For horizontal reaction, assume direction opposing the force at upstream side. Sum forces horizontal equal to 0. Due left equal to due right force. Force that is due left is R sub H, while force that is due right is F sub HU. Therefore, RH is equal to F sub HU, that is equal to 1,589.22 kilonewtons. Next is for vertical reaction. Assume upward direction. Sum forces vertical equal to 0. Upward equal to downward forces. Upward forces are RV and U, while downward forces are W1 and W2. Rearrange, then substitute W1 and W2 as 1,888 kilonewtons and 1,059.48 kilonewtons for U. Therefore, RV is equal to 2,716.52 kilonewtons. Fourth process is the location of the reaction or X bar. Apply summation of moments at the critical point, the toe of the dam, clockwise equal to counterclockwise moments. RV times X bar plus OM for counterclockwise moments, then RM for counterclockwise moment. Transpose OM at the right side and cross-multiply RV, then substitute for RM. The resisting moments are moments due to weights. Then for OM, the moments due to hydrostatic forces. the uplift, and FHU. Substitute values W1 as 1,888 kilonewtons, X1 as 10 meters, W2 as 1,888 kilonewtons, X2 as 16 all over 3 meters, FHU as 1,589.22 kilonewtons, Y sub P as 6 meters, U as 1,059.48 kilonewtons, X3 as 8 meters, and RV as 2,716.52 kilonewtons. Therefore, X bar is 4.027 meters from the toe. Now for the requirements, the factors of safety. First is against sliding or Fs sub S. RH and RV represents the group of actual loads or net horizontal and net vertical forces. Therefore, Fs sub S is equal to mu times RV over RH. Substitute the coefficient mu as 0.6. Net vertical force represented by RV as 2,716.52 kilonewtons, and net horizontal force represented by RH as 1,589.22 kilonewtons. Therefore, Fs sub S is 1.026. Greater than 1 means safe from sliding, but it is already close to a value of 1 means close to critical already. Second is against overturning or Fs sub O. Fso is equal to Rm all over Om. Resisting rotation moments are due to weights, while responsible of overturning moment is the moment due to hydrostatic forces. Then, substitute W1 and W2 as 1,888 kilonewtons, X1 as 10 meters, X2 as 16 all over 3 meters, FHU as 1,589.22 kilonewtons, YP as 6 meters, U as 1,059.48 kilonewtons, and X3 as 8 meters. Therefore, Fs sub O is 1.607. Greater than 1 means safe from overturning, even though it is below the conservative value, which is 2. For the additional part of the problem, determine as well the design pressure at the base needed for checking the bearing capacity of the soil as well as for the design of the foundation. Consider only the value of the vertical reaction RV. Consider the projected rectangular surface of the base, assigning the center of gravity, center of pressure, where RV is concentrated, and distance from CG to CP, the eccentricity E. Apply the equation Q equal to RV all over B times sample length, then multiply to the quantity 1 plus or minus 6E all over B. Solve for E, and E is equal to B all over 2 minus X bar. Substitute B as 12 meters and X bar as 4.027 meters. Therefore, E is 1.973 meters. Substitute in equation the values of RV, B, unit length, and E. Then, first, consider the addition or plus operation. The value of Qmax is 449.749 kilonewtons per square meter. While, if we consider the subtraction or minus operation, the value of Qmin is 3.004 kilonewtons per square meter. Which means that the impact now of the dam is lesser due to the hydrostatic uplift U. Okay, so that's it for the topic analysis of gravity dams. Take care and God bless.